Good afternoon, everyone. Again, thank you for joining us today. On behalf of Aura Network Systems, I'm very pleased to welcome you to our webinar, Airborne Connectivity, Telecommunications, and the Advancement of U.S. Aviation. This webinar is meant to highlight the critical role Spectrum plays in maintaining U.S. leadership in aviation and how that role is dramatically increasing as we're starting to see some emerging technologies integrate into U.S. airspace. I'm Grace Cogburn, Manager of Government Affairs and Policy at Aura, and your host for today. I'm joined by two of Aura's subject matter experts, Brian Regan, Aura's Chief Legal and Regulatory Officer, and Jim Williams, Aura's FAA Regulatory Affairs Director. Combined, they have decades of expertise in spectrum, communications, and aerospace. If you're interested in learning more about them, their full bios are available on the registration page. And with that, I will turn it over to Brian to get us started.
Excellent. Thank you very much, Grace. I appreciate everyone joining today. To set the stage before we get into deep substance here, this is a chart that I think many of you all will be very familiar with. Want to highlight here the national airspace depends critically on spectrum to function. Aviation has been a user of spectrum for a very long time, since the early days of spectrum utilization. Spectrum for aviation supports navigation, surveillance, communications, all to enable the safe and efficient operation of the aviation system worldwide. That includes things like VHF voice and data comms, navigation, GPS, weather services, ADS-B for surveillance, and lots of other services that exist in the spectrum to support aviation. Historically, and we'll talk more about this later, these bands have been either directly managed by the government or managed on behalf of the government. But as we transition into a new generation of aviation, we need to think a little more modernly about how we think about spectrum as well. Grace will go on to the next slide. Fundamentally, communications and the enabling spectrum for communications are critical to the next generation of aviation. As we've seen an evolution of technology where essentially all new hardware and software relies on some level of communications and spectrum to function appropriately, the next generation of aviation is the same. Without these new communications technologies, without access to new spectrum, these services literally won't take off. And that is ultimately Aura's mission. We are coupling our communications and aviation expertise to build the next generation of technologies, spectrum, and hardware to support this evolution of aviation. Aura itself leverages a unique piece of spectrum in the 450 megahertz band. We're designing new ground stations and airborne stations. We've got a 5G core, a cloud-based network management system and platform, and a robust frequency coordination system that's really essential for the next generation of aviation. And we're designed to work within the FAA rules to provide pilots with command and control, detect and avoid capabilities within a private network that's predictable, reliable, and deterministic. I will turn it over to Jim to talk about the background on telecom and advanced aviation.
So you now begin to get an appreciation, I think, for how critical spectrum is for the aviation business. I mean, a large portion of my career at the FAA was spent dealing with communications technologies and the slow advance of them in the current aviation system. But what's it going to take to get the new entrants in? Next slide. So I don't know about you, but I want to be one of these people. I want to be riding on one of these new aircraft and being able to zip around downtown. You know, I was a big fan of the Jetsons when I was a kid, and so it's great that I'm beginning to see that this is actually becoming reality. But these aircraft are challenging the system. They're very different technologically, and they have very different operating profiles to most aircraft. So during my 40 plus years in aviation, automation has been increasing and increasing ever more. You know, aircraft when I first started in the business required 4 crew. Now we're down to 2, and they're talking about reducing that to 1 for the major air carriers for certain situations. So there's, you know, this push toward automation has been going on, and now we're looking at aircraft that are remotely piloted. Now, and what does that mean from a spectrum standpoint? Well, it means that the pilot has to be able to interact with the aircraft, even though they're on the ground. And the only way to do that is through radio frequency link between the ground and the air. And that spectrum for that is one of the needs that exists today and is going to enable these. Also, these aircraft, in order to operate without the pilot on board, have to be able to detect and avoid other aircraft in the environment the same way a pilot would by seeing and avoiding them. Those systems also require spectrum for the most part. So next slide. But it's not just the urban air mobility aircraft, the air taxis that we're talking about. There are several different verticals here that are all going to be pushing the system and requiring additional capabilities both on the ground and in the air. Air cargo. There are companies like X-Wing and Reliable Robotics who are turning existing small cargo aircraft into remotely piloted aircraft. Why? Well, there's currently routes that are being served by trucks because it's just not cost effective to fly even an aircraft the size of a Cessna Caravan between their distribution hubs in these remote areas. By remotely piloting the aircraft and eventually allowing a multiple aircraft to be managed by one pilot in command, you can now achieve the cost ratios required to make it viable to serve those environments with remotely piloted aircraft. Urban air mobility, talked about that already. That's the air taxis that we're all wanting to ride on. But linear inspection, right now, I'm sure everyone has heard about the horrible wildfires that have been caused by power lines being knocked down during windstorms. Well, the power companies want to inspect those lines. They want to inspect them much more often than they do today. Right now, they're only required to inspect them once a year. It's done with helicopters flying low and slow, which is a very hazardous operation. The idea, if you can do it with automated aircraft, you can reduce the cost and increase the frequency and help reduce that risk. Same with pipelines, to avoid spills. By flying the pipeline more often, you can detect a spill quicker. So linear inspection is huge, and the FAA's rulemaking coming out hopefully later this year is going to directly address that particular technology. There's also helicopter operations, delivery helicopters that do crop application, helicopters that do these linear inspections. So again, more and more capabilities at lower cost and a higher safety can be achieved with uncrewed aircraft operations. Next slide, please. So I've mentioned it several times, but the bottom line is the law and the FAA regulations that implement that law require there to always be a pilot in command. Okay, well, how can a pilot on the ground be in command of an aircraft in the air? They have to have a command and control link. So consequently, there is now a new spectrum demand to provide, highly reliable, high integrity links that will allow those operations to take place in the airspace. So part of the process to create these standards, to create these new systems, requires standards. We have to know what performance is required for these links so that we can design them and maintain the right level of safety. And that work has been done to a large part by the RTCA, which is a standards development organization based in Washington, D.C. I co-chair the committee that is responsible for these standards. And since 2012, we've been working on standards for command and control links and detect and avoid systems, both from the standpoint of the overall system and specific types of links. Next slide. So for command and control links, there's quite a few options available, but none of which up until recently have been designed specifically for this purpose. Satellite systems have been around providing voice and data communications to aircraft for a very long time. It's mostly been used in oceanic environments. The cellular systems have been out there, but have not typically been used on aircraft because of the limitations of those systems. Understand that the market for a cellular system is on the ground, so the antennas point to the ground. And I think Qualcomm did a study and determined that above about 1,000 feet, coverage begins to get very sketchy and very difficult to be determined what kind of coverage you have. So it is used though by the delivery folks, both Amazon, Prime Air, and Alphabet's Wing are using cellular connectivity for their aircraft. So there is a place for it. The problem is the cellular system isn't very deterministic. I don't think any of us would want to have a drop call as our aircraft was coming into land or flying into an airport. And so that's where you get into the higher risk situations where you need a system that's more deterministic, that meets certain criteria. So what are those criteria you say? Well, next slide. We spent a lot of time at RTCA trying to answer that question. What is the risk of losing a command and control link? How does that risk translate into design requirements for the aircraft and the airspace? And we've categorized these requirements in sort of 4 broad categories. Availability, that's, you know, can I reach the aircraft when I need to reach it? Can the aircraft reach the ground when it needs to tell the pilot something? Continuity, when I'm sending a message, does it get through with a high level of certainty? And then integrity, it doesn't do any good to send a message if it arrives garbled, or it arrives to the wrong aircraft, or it is interfered with through a third, evil third party trying to cyber attack your aircraft. So there's a very high level of integrity required for these operations. And then latency. So the reason latency is so low is that when you're operating remotely piloted, the pilot on the ground still has to be able to talk to air traffic, and for the other aircraft around it to be able to hear it talking to air traffic, so they don't inadvertently transmit at the same time and make neither message intelligible. So that latency requirement that you see on the screen there is driven by the need to relay a air traffic control voice communication through the aircraft. So that time is very challenging to meet. It's also has very low tolerance for variability in that timing. I don't know if you've ever been on a call with somebody, overseas or whatever, where you seem to just always keep talking on the other person. Well, that's because there's too much latency in that call for you to really acknowledge that it is okay for you to start talking. When I was running one of my FAA programs, we did a study to determine, well, how long, how much latency can you tolerate? And it turns out that your average person waits about a half a second to determine that it's okay to start talking, the other person is done. And that number then has to be apportioned amongst all the different possibilities to try to keep away from that magical half second. And that's where that number comes from. So it's based on actual human factor studies and it's incorporated into the standards. You see these other standards are really high. These are 10 to the -5 per flight hour, 10 to the -7 per flight hour. That is for the strictest, most demanding, highest risk operations, like a cargo aircraft going in and out of a busy terminal environment. For the Amazon and the Wing drones that are delivering packages, they have much lower requirements because they have much lower risk. They're much higher levels of automation, and so the C2 links that are appropriate for them may not be appropriate for the air carrier aircraft that we're talking about delivering large quantities of packages for FedEx and UPS between their hubs and remote airports. So finally, just to kind of nail this home, next slide, please. To nail this home, one of the big differentiators between these systems, so SATCOM and cellular systems, are based on when you arrive at the point at which you need to access the system, you may or may not have bandwidth available. So if your cell phone, you're talking along as you're driving along, all of a sudden you drop your call. Well, what's happened is you've driven into a cell where resources weren't available to support your call. So you were disconnected because there was no way to, the tower wouldn't let you connect. That might be fine for a small drone doing deliveries, but it wouldn't be fine for your aircraft flying into an airport, mixing it up with the crewed aircraft and passenger crewed aircraft. So companies like Aura and others are going to provide a deterministic solution that will make sure that when you fly, your aircraft, you have a guaranteed resource throughout the flight, so you can achieve those high numbers that we came up with in the standards for command and control links. With that, I'm going to turn it back over to Brian so that he can talk to you a little bit more about the telecommunications aspects of what's going on.
Excellent. Thank you very much, Jim. So y'all may be asking yourselves, what does this all mean from a policy and regulatory perspective? So that's what we'll cover here. As discussed, the advanced aviation requires a new policy evolution in spectrum policy. So you think about historic spectrum policy and spectrum utilization was focused on an old command and control style model, confusingly command and control, where the government managed spectrum for and behalf of the private sector. This had some positive effects at the time. It was an easier way to manage interference, allowed the government to be in control, and minimize the risk of sort of competing applications for the same things. It has lots of constraints. You can't really facilitate technological evolution. Imagine coming up with a new kind of technology and asking the government for permission to deploy it, for example. It's not really the current world that we live in. Through the 80s, spectrum policy evolved into a more market-based structure where the FCC put out broader regulatory structures, and Grace, if you can move to the next slide here, where the FCC put out broader regulatory structures where the market essentially had a much greater control in managing the spectrum. The government still had a very fundamental role in it, but moving to a world in which the government setting broader assignment and allocation strategies, relying on things like auctions to be more efficient in how spectrum is assigned and allocated and managed, setting technological rules that are still very strict and stringent, but allow technologies to evolve within them. And the same is going to be true for aviation. That hasn't happened quite yet. Aviation is slow to evolve in lots of ways for lots of very good reasons, both in terms of aircraft and operations and in terms of spectrum policy. But that's the world we're going to enter for this next generation of aviation, where the market is driving new technology innovation at a faster scale than what was available before. And the government's going to create and needs to create policy structures that facilitate that kind of evolution that relies on market-based assignment mechanisms like auctions that allows for more flexibility within technical rules to facilitate new innovation and allows the private sector to really thrive and advance the state of the art. So what does that mean from a band perspective in spectrum policy? We always talk about bands. On the next slide, we highlight the key terrestrial bands that are at play here for command and control in particular. And as Jim mentioned, command and control is really the fundamental thing for the next generation of aviation. If you do not have robust and reliable command and control that can meet the RTCA standards, you can't have a remotely piloted aircraft. They go hand in hand. So spectrum is really critical to that, which is obvious. There are two bands that are available for this use case. The first is the 450 megahertz band, which is a band that Aura currently holds the rights to. It's an old aviation air-to-ground service band. We currently hold a waiver from the FCC to use this band to support command and control for uncrewed aircraft and have a pending petition for rulemaking at the FCC to finalize those rules pursuant to the Commission's request to make those permanent on a go-forward basis. So that's a band that we have today. We've deployed it across the country, and it's available for use now. The second band is the 5030 to 5091 megahertz band. In the aviation world, you hear people talk about it as the C-band, a little bit confusing because there's lots of other spectrum in the C-band. But for our purposes, the 5030 to 5091 megahertz band. And this is another really great opportunity for access to command and control spectrum. This band was globally allocated at WRC 12, so the World Radio Conference, all the way back in 2012. Was globally harmonized for command and control use cases for uncrewed aircraft. The FCC has an open rulemaking on this and has announced that it's actually circulated in part a report and order for a portion of the band. And it was included in the administration's national spectrum strategy. So really a lot of focus on this. And I think it demonstrates the government sort of focus on the interconnected nature between what's happening in aviation and the communication services and spectrum required to facilitate those things. And as discussed in the last slide, this new band in 5 gigahertz is a new market-based structure. This is a kind of structure where the Commission is going to use modern spectrum policy and apply that to spectrum that's going to be used for aviation, which is a great, I think, demonstration of progress along the path towards modern spectrum policy for aviation. Critically, though, these are the only two bands that are available for these use cases. Now, the upside of that is they're available today. They can be used, they're globally harmonized. They can be used for command and control, at least worldwide in the 50/30 to 50/91 megahertz band. And it's enough spectrum for at least the medium term for these kinds of use cases. Unlike the wireless industry, though, the aviation industry does not have a quote unquote pipeline of spectrum that's lined up that's available for these kinds of use cases in the future. So the core thing here is there's enough here to do what's necessary for the near medium terms. If it goes away, if there is sort of a lot of competition for the C-band for other use cases, for example, that does create a fundamental issue with the ultimate success of advanced air mobility in the United States, and that you wouldn't have enough spectrum to support the industry's required use of command and control for remotely piloted aircraft. So really critical to keep both of these bands available and to continue to move forward with the rulemakings for both of them. And next slide, Grace. We'll talk a little bit about the transition here from the spectrum piece of this to intersecting it with some ongoing work that's happening in the context of the FAA reauthorization. So there are two things that you need as a communication service provider to AAM. You need spectrum and networks and technology. You need to be a service provider, and the spectrum is the key piece of that. You also need an FAA approval to be a third-party service provider to UAS operators. This is going to get a little in the weeds, but ultimately, the FAA, like many things in AAM, does not have an existing process to approve third-party services that are required for flight safety, which is not the FAA's fault. It's part of the evolution of aviation. Historically, these kinds of services weren't critical necessarily for flight safety, and they weren't provided by outside parties. They're provided primarily by the government. Now we're moving to a world in which these services are provided primarily by commercial operators, not by the government or on behalf of the government, and they're using new kinds of technology. So the government ultimately is going to have to approve these third-party services. Without a process for that, it creates a lot of regulatory uncertainty for third-party service providers, for operators, and for the FAA. So in order to improve that efficiency and improve that, improve the processes around this, Congress has in the FAA reauthorization incorporated a requirement that establishes that the FAA should, within a year, create a approval process for third-party services, which is, I think, a huge catalyst to this industry. Will help improve investment and development of new technologies and reduce regulatory friction in the future. I do also want to highlight one thing here that this slide focuses on, which is the distinction between UTM and non-UTM third-party services. And this is a little wonky, but really necessary to kind of tease out. So UTM is a traffic management system that's ultimately probably going to be required for small UAS, particularly those that are going to operate below 400 feet. So it's a dynamic system that can include other third-party services that's used for traffic management of small UAS and will ultimately probably be required for it. It is a kind of third-party service, and it may include other third-party services, but it is not the only third-party service. And the slide draws that distinction between what UTM is in the context of third-party services and non-UTM third-party services. Again, very wonky, but really important in the context of advanced air mobility that relies on or uses or has ConOps that are focused on larger aircraft flying in controlled airspace that don't require UTM. So the key here is two things. One, third-party services are critical and there needs to be a process to approve them. And two, UTM is not a catch-all for third-party services. There's a whole host of third-party services that exist outside of UTM. Last but not least, on the last slide here, what does this all mean to you all from a policy perspective? What's the path forward here in a way in which we can enable C2 for AAM? First two are about spectrum. Third is about third-party approval of processes. The first here is really making sure that the FCC, FAA, the rest of the government and other agencies that might have equities and the industry work together to finalize the rules for networked access in the 50/30 to 50/91 megahertz band. So as mentioned, there's already an ongoing proceeding in this. It's making progress. It's covered in the National Spectrum Strategy, which is fantastic. But there's obviously an interconnection between the timing of availability for the spectrum in the 50/30 to 50/91 megahertz band and an operator's ability to certify their own operations and their own aircraft that rely on remotely piloted connections. really critical for the rules for this band to be finalized and to finalize it across different kinds of use cases. There's two different kinds of use cases that are envisioned in this band. One is for what's called non-networked services. This is point-to-point visual line of sight kind of services. The other is network services, which is sort of traditional wireless communications kinds of licensing and rules and structures in which you would have a flight that goes over much longer distances beyond visual line of sight that requires networked ground stations to be available to provide deterministic command and control to those aircraft. Second is finalizing the rules for AURA's band. As mentioned, we've got access to the 450 megahertz band. Band's available today on a waiver basis from the FCC, and waiting for FCC action on final rules for this band. Again, 5030 to 5091, critical for the industry. This is a band that's also available today, probably on a little bit quicker timescale, and just need final rules for that. And then last but not least, as mentioned, a clear FAA approval process for third-party services. Section 932 in the current version of the FAA reauthorization does cover this, and we're grateful for Congress's support for this provision, and really making sure and working together with industry, the FAA, to create a process for third-party approvals that's clear and transparent and efficient, so that there's a lower barrier to entry, lower regulatory friction, and ultimately providing a catalyst to the next generation of aviation. With that, I want to thank everyone on behalf of our colleagues for joining today.